Hello everyone, Mr. Fawcett here. We are back with another AP Calculus lesson. Today we're going to focus on the relationships between the original function, the derivative, and the second derivative. And we're just going to discuss, if we're given one function, what do we know about the other one, right? If we're given the derivative, what can we tell about both the original function and the second derivative? Before we jump into problems, let's make sure we have these relationships down because then we're going to be working to apply them. There are 16 of them. So pause the video, see if you can state what's going on with the derivative, the second derivative, or the original function based on the statement that they give you. All right, so we're going to go through these rather quickly because we do have a bunch of problems to get to. When f of x is increasing, well, our derivative is positive. Likewise, when f of x is decreasing, our derivative is negative. When f of x has a relative maximum or minimum, our derivative changes signs. It's either going to change from positive to negative, or it's going to change from negative to positive. We can't just say it's equal to 0 or it's undefined, because when the derivative is equal to 0, there doesn't have to be a relative maximum or minimum. Same thing when the derivative is undefined, right? We can have a horizontal tangent here, but there's no relative minimum or maximum. So it has to change signs. When f of x has a point of inflection, our derivative has a relative minimum or maximum. And if you weren't sure about what's going on with the derivative here, you could think about the second derivative. When f of x has a point of inflection, the second derivative changes signs. And if the second derivative changes signs, that's going to mean the first derivative has a relative minimum or maximum. It's the same relationship here. Right? When the first derivative changes signs, when the first derivative changes signs, the original function has a relative minimum or maximum. Well, when the second derivative changes signs, which we know is what's going on when there is a point of inflection, the first derivative will have a relative minimum or maximum. When f of x is concave up, our second derivative is positive. When f of x is concave down, our second derivative is negative. When f of x has a point of inflection, we just talked about this, f double prime changes signs. All right, now we're moving on to f prime. When f prime of x is increasing, f double prime is positive. When f prime is decreasing, f double prime is negative. When f prime has a relative minimum or maximum, well, f double prime changes signs. You'll notice that these are the same relationships that we had for the original function and the first derivative, because they share the same relationships as the first derivative and the second derivative. When f prime has a point of inflection, f double prime has a relative minimum or maximum. When f prime changes from negative to positive, f of x, we'll change color here. So when the first derivative changes signs from negative to positive, f of x, still didn't change colors. Well, it has a relative min. We'll get there eventually. When f prime changes from positive to negative, f of x has a relative max. And when f prime has a relative minimum or maximum, f of x has a point of inflection. Oops. Okay, there are two more down below, so I'm going to erase all this and we'll get there. Last two, when f double prime changes from positive to negative, well, f prime has a relative max. And when f double prime changes from negative to positive, f prime has a relative min. Okay, this lesson is going to be all about understanding these relationships and applying them to a variety of different problem types. We're going to skip the graph sorting activity. We're going to do that in class. That would be kind of difficult to do on the video. We're also going to skip this graph drawing exercise as well. And you know what? We're actually going to skip these three graph questions as well. We will do those in class. Let's go down here to the calculator active questions. This first question is 3 parts, A, B, and C. We're given a function. We're given the derivative of a function. And we are asked to figure out if it has any relative maximums or minimums on the open interval 0 to 10. And if it has any points of inflection on the open interval 0 to 10. So I'd encourage you to pause the video, give this one a shot on your own, and then come back and see whether you were able to answer all 3 parts correctly. So if we're trying to find, and we have to remember this is a calculator active question, so we will be able to use that. If we're trying to find a relative maximum, well, we're trying to figure out where the derivative goes from positive to negative. So the easiest way to do this is not to try to set this equal to 0 and solve. It's calculator active, so we are going to graph it on a calculator and look at where it goes from above the x-axis to below the x-axis. Let me pull up my calculator and we will punch this in. All right, so I've typed in my function. I'm now going to set my window to go from 0 to 10, because that's the only values I care about here, that interval. And I'm going to hit graph. So we can see that it crosses the y-axis twice on this interval. And we can actually change our y value, so we go from -5 just to 5. That way we'll be able to see it a little bit better. There we go. Could even just go, you know what, why don't we make it better? Let's go from -2 to 2. Sometimes it's just nice looking at a better window. There we go. So we're trying to figure out where it goes from positive to negative. So we need to figure out, you know, where it crosses the x-axis here. And we're not going to guess. We're going to round it to 3 decimal places. To do that, we are going to go to second trace, find the zeros, option 2, go a little bit to the left of the 0, hit enter, go a little bit to the right of the 0, hit enter, and then let the calculator do the guesswork. Our 0 is at approximately 4.810, whether you truncate it or round. So that's what we would put. And that's the only one. We would say, let me get my pen out, f of x has a relative max at x equals and we should actually say approximately 4.810, because f prime goes from positive to negative here. And we would do the same thing for the relative minimum, except we're looking for the opposite. We're looking for where it goes from negative to positive. So let's pull that up. Move this down. We're going to find another 0. It's going to be the one way over here. To the left. To the right. Let it guess. And it's approximately at 0.208. I'm going to round to 3 decimal places rather than truncate. So f of x has a relative minimum at x is approximately equal to 0.208, because f prime of x goes from negative to positive here. Now we need to figure out where the original function has a point of inflection. Well, points of inflection occur where the second derivative changes signs. We're only given the first derivative, though. So you could go back up to your list at the beginning, right, and find out, if we're looking for where f of x has a point of inflection, find the arrow that points to the first derivative doing something. But you can think about it in terms of the second derivative as well. If the second derivative is changing signs, that means that the first derivative is going to have a relative minimum or maximum. So we need to look. Let's get rid of that. Let's give ourselves some more space. Where does this function have a relative minimum or maximum on the interval 0 to 10? Well, it looks like it's right about at 1, but let's make sure. This time we're going to do maximum to the left. Make sure you get all the way over so you're sure that's on the other side, and let it guess. And it is at x is approximately equal to 1. If we round to the nearest thousandth, right, it's still going to be 1, because that 9 is going to bump up the next 9, which bumps up the next 9, which bumps up the next 9 to a 1. Still approximate, though. And we would say f of x has an inflection point, or point of inflection, now, when you're rounding, you still would put 1.000. That shows that you rounded to the nearest thousandth, because f prime of x has a relative max at this x value. And that will finish up question number 1 for us. Let's move on to the next one. It says, on the open interval 0 to 10, how many relative minimums does the graph of g of x have if g prime of x is equal to sine of x divided by the quantity x plus 2? Well, if we have our derivative and we're trying to figure out where our original function has a relative minimum, think about what has to happen with the derivative. Well, it's got to go from negative to positive. So again, we can graph this. Same idea as before. Let's pull up our graphing calculator. Make sure your calculator's in radians. Make sure you put your denominator in parentheses. All simple stuff, but could throw off your answer. Again, we're looking for where it goes from negative to positive, because that would be a relative minimum. So it looks like it's somewhere near between 7 and 8. Let's make sure, though. Second trace. Looking for that 0. And that occurs at approximately 6.283. And you know what? I initially looked at this question a little incorrectly. I was thinking we were trying to figure out where the relative minimum was. However, we are trying to figure out how many. So didn't even have to do that. Sometimes you're doing extra work. We only had to identify how many times that graph crosses between 0 and 10. Now, we do have to be careful. It does look like it crosses right at 0 here. However, we need to make sure that that doesn't cross just after 0. Because if it crosses just after 0, it's also going to be in the open interval. So, again, this could be tricky if you just kind of assume that that goes right through the origin. It wouldn't count. But if it's slightly to the right of the origin, it would count. Let's quickly just check. We know there's at least one. And it crosses right at the origin, so that would not count because that would not be on the open interval 0 to 10. It would only be on the closed interval 0 to 10. So our answer would be B. There's only one time where the derivative goes from negative to positive. I think you can probably tell that I created this lesson well before I did this video, considering I didn't remember the question that I had put down. That being said, sometimes you just need to read a little bit more carefully, and that includes myself as well. All right, let's move on. We have a table here, and it says the derivative g prime of a function g is continuous and has exactly 2 zeros. So those zeros are given in the table. Selected values of g prime are given in the table above. If the domain of g is a set of all real numbers, then g is decreasing on which of the following intervals? Well, if g is decreasing, we need to think about what's going on with our derivative. Right? Go check your chart, or go, better yet, just think about it before you check your chart. Save your chart for emergencies. Well, if the original function is decreasing, our derivative is going to be negative. So we need to find some negative intervals. Looks like that interval is right there. -2 to +2. And that's the only one, right? If those are the only 2 zeros, well, then we know on this interval, it's always going to be positive, the derivative, as well as this interval. Because if one value is positive on that interval, they're all going to have to be, because there's no other zeros. There's no more times where the derivative crosses the x-axis. So A would have to be correct here. Let's move on to the next one. The second derivative of the function f is given by f double prime of x is equal to x times the quantity x minus a times the quantity x minus b squared. The graph of the second derivative is shown to the right. For what values of x does the graph of f prime have a relative maximum? Well, if we're given the second derivative and we want to know where the first derivative has a relative maximum, you could think of it as, well, what's going to happen? Well, you could think of it as a original function first derivative relationship, right? If we're looking for where the original function has a relative maximum, the first derivative would have to go from positive to negative. Well, if we're looking for where the first derivative has a relative maximum, then the second derivative would have to go from positive to negative. we have to think about where that occurs. And looking at the graph, A is the only time where the derivative does that. It goes from positive to negative. So C would be our answer here. At the origin, it's going the other direction, so we'd have a relative minimum of f prime. And at B, we would have neither because the second derivative is not changing signs. It goes from positive to positive. I believe we just have one more because we are not going to do the last question on here. It says, if h of x is a twice differentiable function such that h of x is less than 0 for all values of x, then at what values does the graph of g of x have a relative maximum if g prime of x is equal to the quantity 9 minus x squared times h of x? Pause video. See if you can figure this one out. So to figure out where g of x has a relative maximum, we need to figure out where the derivative goes from positive to negative. And it might be helpful if we knew where the derivative was equal to 0. And then we could think about a number line. All right, if this represents g prime of x, then we can find our critical values. G prime of x is going to equal 0 when either of these factors are equal to 0. That's going to occur at -3 and 3. And h of x is never going to be equal to 0 because it says that h of x is less than 0 for all values of x. So let's think about it. If we chose an x value, let's say g prime of -4, well, this factor right there would end up being negative because we'd have 9 minus 16, which is negative. Then we're multiplying it by h of x, which is always negative, so we'd have a negative times a negative, which gives us a positive. If we had g prime, we'll say, of 0, well, that would be 9 minus 0, which is positive, times a negative number, which is negative. And if we had g prime of 4, that's going to be the same as -4 because I'm squaring it. So I'd get 9 minus 16, which is negative, times h of x, which is always negative, which gives me a positive. So the only relative maximum would occur at x is equal to -3 because that's the only critical point where g prime goes from positive to negative. Okay, we are going to cut the video there. We will discuss some of the other problems during class. We'll talk about the relationships as far as looking at those different graphs. We'll do the graph sorting activity and the graph drawing activity. But as always, enjoy the rest of your day, and I look forward to seeing you next time.